Welcome everyone. In this video I'm going to show you how to compile and execute your VHDL projects in your own PC. Alright, so let's get started. As you can see, I'm using a Windows box for this. However, I'm going to be using the Linux environment because it's the easiest way to install the tools necessary for this. In order to compile and execute our VHDL projects, we need three pieces of software. One is a text editor, which you can get anywhere, and there are plenty of them. Just like Notepad will be enough. However, it's probably not the best one that you can get. Something like a programming IDE like VS Code or any other that you're comfortable with will do the work for you because it offers a lot more functionality. And more importantly, syntax highlighting, which is the best for programming, right? However, like I said, I'm going to be using the Linux environment on Windows, which in this case, in order to get it, you need to install WSL. I'm going to assume that you already have it installed. If you don't, then I can make a video on that on a separate occasion. But for now, I'm going to assume that you have it installed and you have a Linux distribution in there. So I have Ubuntu running here, and this is what we're going to use. But before that, let's talk about the tools that we need in order to execute our files. So the first thing, as I said, is the text editor. We got that covered. Other than that, we need a VHDL compiler. In this case, we're going to be using GHDL, which is the open source compiler of choice for VHDL projects. And as you can see, well, here in the description, it's a very powerful tool for writing, testing, and simulating your VHDL code. GHDL, as I said, is open source software, so you can actually go into the GitHub page and you can look at the source code, you can look at all the information there, you can actually download it and build it for any different platform that you want, if you know how to do that. Otherwise, you can just follow the instructions on the video. Then the third piece of software that we need is the waveform viewer. It's a waveform analyzer. This allows us to visualize in a graphical way the results of our simulation. In this case, we're going to be using GTKWave, and as I said before, or now, this is also an open source tool, so you can download the source code or you can see it in GitHub as well. It builds for all the platforms, although the process of installation might be a little bit more complicated depending on the platform. However, if you're using the Linux environment or the Ubuntu distribution, which is what I'm using, installing these apps is very simple. So all we have to do is come and do apt install GHDL and GTKWave, and that's all we need. So with that, we can just install it, and it only takes a couple of seconds. And this is one of the main advantages of doing this instead of installing proprietary compilers, because usually they come bundled with a bunch of other tools that we not need, and they are not universal. So in this case, that's all the time it took for installing all the tools, GHDL and GTKWave, and we can do GHDL -- version, and we can look at the version there. That means it's properly installed, and GTKWave -- version as well, and we can see the version of installation. So one thing that's very important is that this installation process does not leave you with the latest versions, and that's why I mentioned that the source code is hosted on GitHub, because that way you can download the latest version, you can build it for your own platform if you know how to do that. And if you don't know how to do that, then you can, that's probably a good exercise to do in learning how to build software from source. But for this example and for the projects, if you're not simulating giant projects or that are using the latest language features, or if you're not a power user of any of these systems, then you don't really need the latest version. So now that we have installed our tools, we can move on and we can start writing some design. So I already have set up some code here. Let's look at these files. So I got some extra files here. Let's get rid of them. And let's do like that. So we have two files in this folder. It's a counter.vhdl. This is a design for a counter. And we have a test bench, counter_tv, for our test bench. So let's look at the counter file. All right. So I'm using NeoBeam. As I said, this is my IDE, but you can use any other editor. It's just as good. So in this case, our entity is called counter, and it has a couple inputs as a reset and a clock input, and it has the count output, which is a 32-bit vector. We have a generic value here. There's this top count, which means it's the highest value at which the counter is going to, or count to. And if you would look at the architecture, we have an assignment here, and the main process here is basically executing on every rising edge of the clock. If the count has reached the maximum value or reset is equal to 1 when the rising edge comes, then the count gets reset, otherwise it just increments by 1. Now it's important to notice, just a small detail, but since the reset is inside this block, that means that we have a synchronous reset, meaning that it will only happen at the rising edge. It's not an asynchronous reset, which was more popular, I guess. That would be the proper way to phrase it. Okay, so now let's look at the counter test bench. So the test bench also is very simple. The name of the entity is counter_TV. You should remember that because it will be important in the near future. And we can see here we're just declaring a couple signals. We're implementing the counter here as our unit under test, and we have a main process here, or a clock process, that is just having a clock that with a period of 4 nanoseconds, and then the main process of the simulation is just sets the reset to 1, waits for 5 nanoseconds, releases the reset, and then it waits for 500 nanoseconds, and then that's it. So very simple code. This is not meant to be complex because I'm trying to show you how to compile this code into a executable simulation. So let's go back out into our main folder, and this time we're going to use GHDL to compile our file. So the first thing that we're going to do is do GHDL-A. The command -A means analyze, and this is the command that will basically compile your code into a working library. So in this case, we're going to compile first the counter file, and when we do that, nothing comes back at us because if there's no errors, then there's nothing to see. But if we look at the folder structure, you can see that now we have this file called work-object93.cf. This is basically the compiled version of the counter, and this works as a library where the counter becomes available for other entities to use. So now we can go ahead and compile as well the test bench. And again, we don't get any errors. If we look again at the folder, nothing has changed because this the compile object also goes into the work object or the work library that we have created at the beginning. Now, I'm going to remove that file just from now because I want to show you something very important. And something very important to keep in mind when you're working with VHDL is that VHDL is a hierarchical language, meaning that the structure of your project depends on a hierarchy of different components. So when you compile or when you make your project, if you're familiar with making or with building C projects, this is very similar because we need to compile the objects and the files in a certain order. So in this case, since I deleted the work library, we're going back to the original setup that we had the folder as. Let's try to compile the test bench first. As you can see, I get an error message in this case because the unit counter is not found in the library work because we have not compiled the counter file first, and the test bench is implementing the counter here in this line that is showing here. So because this has not been compiled yet, then we're getting this error. So we need to compile first the counter. So we're going to go and compile the counter first, and then we're going to do the test bench. Now, when you analyze files, you can pass multiple files in one line, but keeping in mind that the hierarchy will go from the bottom to the top. So you'll start with the lowest hierarchy components first and working your way up to the top. In this case, because we only have 2 files, the lower entity would be the counter and the higher or the top level entity would be our counter test bench. Then that way we can compile both of them and we don't get any errors. All right, so we're going back to the main to what we had before, where the library has been compiled successfully. And now we can proceed with the second step. The second step is the elaborate step, which will take all the components from the library, or not all the components, but the ones that are being used in the simulation, and it will link them together. So for that, we do GHDL-E, and this time we will pass not a file, because we've already compiled the files, but the name of the entity that we want to elaborate. In this case, if I remember correctly, it was counter_TV. We can elaborate that, and that's it. That has created the object necessary for running the simulation. And now we can do the last command on the last step, which is GHDL-R, which stands for run. So now we're going to run the simulation. We're going to pass the name of the entity, in this case the same test bench, and there's many flags that you can add here to tailor the simulation to your liking. I'm just going to show you a couple. So in this case, I'm going to use stop time, and we can set the limit. This is a limit for the simulation. I want to run the simulation for a certain amount of time. So I could do 1 second, but 1 second is way too much for what I want. If you remember, the test bench had a period, the clock frequency had a period of 4 nanoseconds. So in this case, 1 microsecond will be plenty of time for us to see the behavior of our design. And then I'm just going to add another flag called VCD. This will be the format of the output that we want the simulation to come out as, and I'm going to call it out.vcd. You can give this file any name. So after that, we get message here, say simulation stopped by stop time. This is because we entered this flag here, and it was stopped at 1 microsecond. So now, if we look at the folder again, we have created a file called out.bcd. This is the simulation, or the results of the simulation. So if we look at this file, and we look at the contents of the file, you can see that there's a couple flags here at the top, some variable declarations, and a bunch of data with some numbers that are very hard to understand what's going on here. However, this is why we need the waveform viewer, because if we now use GTKWave and we pass the name of the file that we had the output for, then we can just look at that in our graphical interface. So as you can see, this is GTKWave. Here we have the timing window, and on the left here we have the unit of the simulation. In this case, it's the test bench for the counter. When we click on it, we can see the signals that appear here. These are the signals that are being declared in the test bench. However, if we click on this little triangle here, we can see the hierarchy of the project. In this case, the counter test bench. It's implementing the UUT device, which in this case is the design under test, or the unit under test, which is the counter. And as you can see, when I click on it, the signals here change, because now these are the signals associated with the counter itself. So this is what I want to see in this moment. So I can select them one by one, or I can press Shift and click around and select them all. And if I right click on it, I can append or insert. This is basically the same, it's just that append will add it to the end of the list. So I'm just going to insert all of these signals here, and as you can see now, they appear there in the timing window. And however, you can see that this is very zoomed in. So we are only seeing here about 8 femtoseconds of simulation. So there's nothing to see here really, it's too short. So we can use these controls here at the top to zoom out. We can zoom out like that, or we can hold the control key and use the scroll wheel to zoom out. Either will work. And now we can see the behavior of the counter. So we can see that on the rising edges, the count increments by 1, and it goes all the way up to 9, and then it goes back down to 0. Here, when the reset is held high, it doesn't change, and that's basically it. So now in the window itself, we can see different things. For example, if we select signal here, we can use these little arrows here to move around in the different every time that the signal changes, we move around, and we can zoom with the right button. We can zoom like that. If we just hold it and release it there, we can zoom into the simulation as well. As you can see here, this count output is a binary vector of 32 bits, but the numbers that are being displayed here are integers or integer or natural. So if we want to change the format and we want to visualize them as a different value, we can right click on it and change the data format to, and then we have lots of different values. In this case, I'm just going to go and change it to binary, and now you can see that it shows me every single bit. So I'm going to zoom in a little bit so we can see the entire thing, and there we go. That is how we can change the format of the data. We can also assign different colors to the signals. That's just so that we can differentiate them and make our simulation a little bit easier to read, especially if we're manipulating many signals or if you're checking different things at the same time. So that way we can keep our simulation very nice. So that's it. I hope this was helpful, and in the next videos we'll be going a little bit more deep into some other projects, into some VHDL coding, and into some more aspects of GTKWave and GHDL. So good luck, and on to the next one. Bye.